Let me proceed on to IP-based routing as well as IP addressing, and I'll also include subnetting. Now, since the internet is built on IP-based communication, this type of communication essentially allows devices to be able to uniquely identify themselves across the internet, as well as to be able to send data, you know, um, across the internet or across a network, right? So they are fundamental, both IP addressing and routing. They're fundamental in making sure that information reaches the correct device anywhere else in the world. So looking at IP addressing, an IP address as an internet protocol address, remembering the first video where I spoke about the internet protocol, that the internet uses those communication protocols such as TCP as well as the internet protocol. So an IP address is an internet protocol address, which is a unique numerical identifier that is given to each and every device which is connected to a network or connected to the internet, which allows devices on the internet to be able to communicate with each other, to be able to send and receive data. Um, over the internet, as well as those devices. Any type of device can be mobile devices, IoT devices, billions of devices, laptops, whatever you name it, right? To it allows them to be located over on a network topology or within a network topology. So these IP addresses are fundamental because without them, data cannot be accurately um, uh, routed to the correct destinations or to the correct devices anywhere else in the world. So now there is two important versions of IP addresses. One is the IPv4, also known as the Internet Protocol version 4, or the fourth version of IP addresses, right? So that version uh, of IP addresses has like an address land of like 32 bits, which would be equivalent to 4 bytes, right? And a typical format of that uh, of IPv4, or yes, I'm gonna call IPv4 instead of Internet Protocol version 4. So um, uh, the format that it has is there's like four decimals, which are usually separated by which are usually separated by dots. Um, an example is, let's say you have an IP address of one that is like 192.168, let's say point one point zero as well. So those are four uh, uh, not these decimals which are separated by dots. Now each number in this IP address is referred to as an octet, right? And each number usually varies between 0 and 255, right? But we're gonna look into that. Now the typical characteristics or the features of this type of IP addresses, namely the IPv4, is that they have an address space, or the number of addresses is approximately like 4.3 billion IP addresses worldwide. That's like 2 raised to 32 bits. And one thing about these types of IP addresses is that the most common version of IP addresses, like historically for internet communication, right? And these type of IP addresses, IPv4 addresses, can either be public, they can be private, they can be static, as well as dynamic. But the problem with these types of IP addresses is quite obvious, is that there's a limit, or an exhaustion of all available IP addresses, because there's like approximately 4.3 billion unique addresses, right? So there's an exhaustion of these available addresses, which would ultimately lead to IPv6 or IP version 6, right? So it led to the development of IPv6. Now IPv6, or Internet Protocol version 6, has an address length of like 128 bits, which is equivalent to 16 bytes, right? So remember, IPv4 had like 32 bits. This version, or version 6, has like 128 bits. So is quite higher, and the format of IPv6, IP addresses is quite different from IP or IPv4 IP addresses. Uh, so with IPv6, there's like 8 groups of 4 hexadecimal digits which are separated by a colon, right? So imagine an IPv6 IP address that's like let's say 1938, and then colon, and then there's R2 um, 36 colon uh, 0000 colon, and so on up to um, the eighth group of these 4 hexadecimal digits, right? So we have that series of hexamal digits, or these 8 groups of 4 hexamal digits. That's a typical V6 IP address, right? And the typical features of IPv6 IP addresses is that the address space is usually or is virtually unlimited because uh, of these of the wide address length, like 128 bits, which would, let's say we take two and raise it to 128 bits. That's virtually unlimited, right? So they also this type of IP addresses, they also have like built-in security support, like IP security, as well as supporting efficient routing as well, right? But uh, to highlight the why uh, IPv6 is actually better than IPv4, you have to consider the fact that IPv6 actually accommodates the growth of the internet, or the growth of IoT devices, of mobile devices, and the internet itself, right? Because it's rapidly expanding. And IPv4, when it comes to something called NET, which is the network address translation, IPv6 is not dependent too much on this network security feature. But IPv4 IP addresses actually depend, or they often use network address translation, right? And IPv6 is actually uh, quite scalable because, as I've said, that more devices, uh, they have more IP addresses, and so it supports the growth of the internet, right? So since I've said previously that IPv4 addresses or IP addresses can be public, they can be private, they can be static or dynamic. Let's look at or compare between public and private IP addresses. Now, public IP addresses are usually assigned by an ISP. Remember the ISP, Global Central, in these videos, right? So it is that any public IP address is assigned, or it comes from an internet service provider, and it's globally unique for each and every device, and it is routable on the internet, can be sent to the backbone networks and so on, right? So it is also used to identify devices to external networks, like let's say the servers within a data center. Remember the servers in the previous video, would be able to identify those servers to the external networks, like the internet itself at large, right? And then the private network. So I've looked at public um, public IP addresses, and then the private um, IP addresses, right? These ones are typically used within local access, local area networks, like home networks or office networks, right? And compared to public IP addresses, private IP addresses are not routable on the public internet. So that's the key difference. And private IP addresses are usually defined by the standards in RFC 1918, right? So you'd have typical address ranges, as well as the use cases of different private networks. Let's say for a large private network, you would have an address range that varies between 10.000, no, sorry, it's 10.0.0.0 up to, let's say, 10.2 55.255.255. That's the typical address range of a large private network. And then for small networks or home networks, an address range would typically vary between 192.168.0.0 up to 192.168.255.255, right? And then considering medium private networks, uh, the typical address range usually varies between 172.16.0.0 up to 172.31.255.255. So that's the typical address range of private IP addresses, right? And one thing about private IP addresses, they usually communicate externally through the NAT, network security feature, or the network address translation feature, right? And then there are static as well as dynamic IP addresses. So looked at public IP addresses, the private IP addresses, then the static as well as dynamic IP addresses. Now, static IP addresses are usually manually assigned and they don't change over time. That's why they're static, right? So given an IP address, it's permanent. It doesn't change over time. And those types of IP addresses, they're usually common, for servers, for hosting various services, for used for remote access devices. They use static IP addresses as well as networking equipment that's in a data center. They use static IP addresses, right? And one thing about static IP addresses is that they are very reliable when it comes to uh, hosting services instead of compared to dynamic IP addresses, because with dynamic IP addresses the problem is that the IP changes periodically, and so that may complicate the hosting um, and the process of hosting services, right? So that's one thing that's particularly good about static IP addresses, that were very reliable when it comes to hosting services. And one thing about them is that you can do easier or easy DNS mapping. But the bad thing about static IP addresses, it comes from the fact of limited flexibility and always requiring manual management. And then there are dynamic IP addresses. Those dynamic IP addresses are assigned by, or you remember static ones were manually assigned, but these dynamic IP addresses are automatically assigned by a server, or DH, um, a DHCP server, or the dynamic host configuration protocol server, right? And so these type of IP addresses, you usually see them on the internet, right? So they're used by home users, more devices, as well as gas networks, right? And one thing about uh, these dynamic IP addresses is that they're easy to manage, and there isn't any wastage of IP addresses. So there is like efficient IP usage with them. And the bad thing about dynamic IP addresses, is I've already highlighted, is that um, these types of addresses tend to change periodically, and so that may complicate server hosting. And they're also less predictable. Let's say for remote connections, they're less predictable in those circumstances. So with like four types of IP addresses: we have public IP addresses, private IP addresses, static IP addresses, as well as dynamic IP addresses. Public IP addresses, they're globally unique and routable on the internet, whereas public, or private rather, private IP addresses are used within local networks, and they also use NAT, the NAT feature, network security feature, right? And static IP addresses, they're permanently assigned. Whereas on the other hand, you have dynamic IP addresses, which are temporarily assigned by or via the DHCP server, or the dynamic host configuration protocol server, right? So those are the different types of IP addresses. Now, these are important. All these IP addresses that I've mentioned, the different types of IP addresses are important, and the importance or their significance lies in unique, identification. That is to say that they ensure that there is unique identification of devices all over the internet, right? Every device can be uniquely identified from the other, and it enables efficient data routing or the routing of data packets to the correct destinations. So you cannot send data packets to the correct destinations unless those data packets have IP addresses, namely the source and the destination IP addresses. Remember, in the earliest videos, I've mentioned that the data packets needs to have or they contain source and the destination IP address. So this these IP addresses they ensure that data packets actually arrive to the correct destination, right? And they're important in that they ensure that they use like and we call this um, um, they support like hierarchical network design, let's say from local networks to regional networks up to global networks. You don't need to redesign the entire network IP scheme, right? So, and then there's the process of subnetting. Now, subnetting is it goes along with IP addresses, but let me explain the process of subnetting. Now, subnetting is very important when it comes to IP networking, right? Because now it allows administrators to essentially divide a larger network um, into smaller, more manageable segments, and those segments are called subnets, right? So you're subnetworking or dividing a larger network into subnets, right? And the reason why this is useful or it's a useful practice is to improve efficiency, and we're going to look at that efficiency. How is that efficiency achieved? You there to use this process also improves things like security as well as organization or management in IP-based networks, right? So subnetting, what it is a process of whereby you split a network or larger or single IP network into smaller or multiple smaller logical networks. Now, each subnet from this larger network, each subnet actually functions as an independent network, meaning that it contains its own range of IP addresses, right? So subnetting is uh, the process of subnetting or is both efficient as well as effective. Efficient in a sense of IP address utilization and as well as effective in terms of network management. Now, in order to picture or like understand the process of subnetting, you think of a large city which can be taken as a network, and obviously that large city would be divided into different neighborhoods, and those neighborhoods can be taken as a subnet, right? Now each neighborhood or each subnet would have its own host, or the its neighborhood would have its own houses, which in this case would be considered as host as well as subnet routing or local roads, right? So that's a way to think about uh, the subnetting process. Now, the point of subnetting is lies in the fact that you want to have efficient IP address utilization. That simply means that there isn't any wasting of IP address. So subnetting actually prevents the waste of um, IP addresses on like small networks. It reduces because there can be unused networks, or rather unused IP addresses on larger networks. So it reduces the number of unused IP addresses on large networks, right? And it also improves network performance in that there's a reduction of like broadcast traffic within each subnet. And I'm going to explain what this broadcast traffic relates to when it comes to subnetting, right? Not only that, there is an improvement or enhancement of security, because now the traffic between that that flows between between subnets can actually be filtered using firewalls, or you can use access control list or ACLs, right? So subnetting also simplifies network management. How? Because now with subnetting, it's easier to assign IP addresses for different departments, different buildings, and as well as devices. Now, why am I mentioning departments or buildings or what? Where do they fit in? Because remember, there's different traffic that flows from different departments and services, right? So subnetting are actually dividing the traffic that's flowing from these different departments and services and so on, so that there is more security, so that there's no like eavesdropping, or um, people seeing what they should not see, or having like uh, access to information they should not have access to. So that's why there's um, this limiting of broadcast traffic, right, from different departments, services, and so on, right? So um, subnetting, it makes it easier to assign IP addresses to these different devices, department networks, and so on, as a building networks, whatever, office networks, and so on, right? It also facilitates something that which is very common, network monitoring as well as troubleshooting, right? So that would be the point or the whole point of subnetting, right? And then there is a method called CIDR, that is the classless interdomain routing method, and that is a method that is widely used in order to allocate um, IP addresses as well as routing IP packets, right? So this method is preferred over the old class-based system, like Class A, Class B, and Class C, right? So this type of method, CIDR, actually uses network prefix length, and that network prefix length is used to indicate the number of bits for that I have been used for the network portion of an IP address. So the CIDR has a particular notation whereby you have, let's say, on the left hand side you have an IP address, and on the right hand side, which is separated by a forward slash, on the right hand side you have the prefix length. So to put that into context, to consider an IP address like 192.168.1.1 forward slash 24, right? That forward slash 24 is the network prefix, right? And it's used to indicate, it tells us that the first 24 bits actually are the network portion, and the remainder 8 uh, bits actually are for the host portion. So an IP address has two parts, right? The network portion and the host portion. Remember that this IP address that I've just mentioned now, it's an IPv4 address, right? And an IPv4 address has 32 bits as or the address length of IPv4 IP addresses is 32 bits, right? So that's why you have the first 24 bits belonging to the network portion, and the remainder, or the last 8, belong to the host portion, right? So this method of CIDR is it helps when it comes to reducing the size of routing tables, and does so via aggregating routes or routes, right? But we're gonna look into that going forward, and it's also there to support things like subnets or subnets with variable length, or VLSM subnets, right? Those are subnets that have the varying lengths. And moving on to the the two portions of an IP address, uh, the network portion or the network prefix as well as the host portion. So we know that an IP address has now like is divided every IP address or every IPv4 address is divided into two parts, right? The first part is the network prefix or the network portion part. So it's can either be called a network prefix or the network portion. It's the same thing, right? So that's the one part. Then the other part is the host portion of an IP address, right? So the network portion or the network prefix identifies the subnet, right? And all the devices within a subnet actually have the same within any subnet, right? So we divide the network into these different subnets, and each subnet has its own devices that are connected via through that subnet or that are connected to it. Now, each and every device within a subnet have the same or they share the same network prefix. Remember that /24, that's the network prefix that I'm referring to, right? And this network prefix can either be determined by the subnet mask, as I'm going to look at it just now, the subnet mask or the CIDR prefix, right? And then there's a host portion. The host portion, what it identifies all the individual devices within the subnet, right? So it is unique for each host in the subnet. This host portion is unique for each host in the subnet, and the number of host addresses would usually depend or are determined by the number of bits in the host portion, right? Now, to put this into context, you consider again an IPv4 address, IP address subnetting, right? Let's say you have a network or an IP address, like I'm gonna keep it simple and use the same IP address, right? Let's say 192.168.1.1, right? Slash 24, right? So that's an IPv4 subnetting. Now the network prefix in there is the first 24 bits, right? Those are determined by 192.168.1, and then you have the host portion. The host portion is the last 8 bits, um, in the for the host portion, and those are determined by the range between 0 and 255, right? So in between 0 and 255, you have like 254 usable addresses, right? You have 254 usable hosts, and the 0 would indicate the network address, whereas the 255 would indicate the broadcast address, right? So whenever you have this host range or the host of addresses between, let's say, between 9 and 26, so 9 would be the network address, and 26 would be the broadcast address, right? So that's how it works, right? Now, subnet mask, moving on to subnet mask, they are there to define or tell us which part of an IP address is a network portion and which part of an IP address is the host portion, right? And it uses the same decimal notation of IPv4 addresses, like let's say an example would be, let's say, 255.255.255.0, and then that has an equivalent CIDR notation, which would be that /24, right? And how submask, oh, not submask, subnet masks work. Subnet mask work is that the zeros, those binary zeros and ones, how they work is the zeros in the subnet mask would actually represent the network bits, and the ones would represent the no, the ones in the subnet mask would represent the network bits, whereas the zeros, that's what I'm trying to say, whereas the zeros in the network in the subnet mask are there to represent the host bits, right? So the common subnets or IPv4 subnets that are let's say you have uh, a CIDR prefix, let's say slash 24 or forward slash 24, and a subnet mask of like 255.255.255.0. In that case, the network bits would be like 24 bits, and the host, uh, um, no, no, the yes, the network bits would be 24, and then the host bits would be the remainder, namely 8 bits, right? And in between 0 and 255, you have 254 usable um, addresses or usable host, right? And another, let's say, CIDR prefix, take for example, slash 25, right? In that case, maybe the submask that is equivalent to that is 255.255.255.128, right? The host bit in that scenario would be, or the network bit in that scenario would be equivalent to that slash 25. So the network bit would be 25, and the the host bits would be the remainder, namely 7 bits, right? So in total, you have 32 bits for all these IPv4 addresses, right? So that's why you have 25, and then the remainder or the host bits would be 7, right? And then um, the usable host would actually be like 126, right? And you can go on and on and on and on and on and on, right? For let's say I go on to slash 26, the CIDR prefix is like slash 26. Then you have um a subnet mask of 255.255.255.192 and so on. The network bits in that case would be 26. The host bits you would be um, would be 6, right? That's the remainder. There would be 6, and the usable host would actually be 62. So you get the trend, right? So uh, the CIDR prefix determines the network bits, and then you have the remainder of the host portion, and so on and so on and so on. So now, uh, outlining the process of how subnetting works, step by step, we actually first have to determine the total number of addresses which are needed for the host. That's the first thing that you have to determine. Next, you have to choose a subnet mask slash CIDR, right? But that would actually be able to provide at least that number of host addresses, right? So first to determine the total number of uh, of host address of host addresses that are needed. Then you choose the subnet mask slash the CIDR, which would actually provide that number of host addresses. And then after that, how you divide the network is into subnet is you actually use the host bits, right? And I'm gonna explain just now how you use the host bits, right? And then from there you assign the addresses to each subnet, or the address length or the host to each subnet. And finally, you actually configure the routers to route traffic if there's any need, right? So in order to put this into context of how this subnetting process that I've just explained, whereby you determine the total number of host addresses that are needed. Uh, let's say you have a network or an IP network of 192.168.1.0/24, right? So let's say you need like 4 subnets, right? So you borrow because now you have to divide the network into subnets, right? So you borrow and you use, in order to divide the network into subnets, you use the host bit. So you borrow two bits from the host portion, right? So you have 26 subnets, right? Now the subnets that are created would be like let's say 192.168.1.0 slash 26. That's the prefix length or the network prefix, right? The slash 26, the network prefix that tells us that the first 26 bits are for the network portion and so on, right? So the the host addresses that you would have um, in that subnet would vary between 1 and 62, right? Because uh, let's say the next subnet that is created is actually 192 0.168.1.64 instead of 0. So you put 64 instead of 0 in there, right? That would have host addresses from 63 all the way to 120, 126 host addresses. And then you go on to 192.168.1 um, 128, right? So you have host addresses that vary from 129 to all the way to 190, and so on and so on and so on. So that's the process of subnetting, right? Now, the reason why subnetting is important lies in the fact that you don't have to design the entire or redesign the entire IP scheme. Let's say there's an experience of network growth or scalability or scalable networks, right? There's no need for you to design or redesign the entire IP scheme, right? And so subnetting essentially or overall divides this large network into different subnets, right? And then you have the CIDR notation, which is there to simplify, and then the network prefix, or they specify that notation specifies um, the network prefix as well as the host portion explicitly, right? And yeah, see you next time. Next, I'll be covering routing fundamentals. See you then. Thank you.